Is this the thing that I should be using?
Yeah.
Okay, thank you. If it works. Famous last words. All right. Well, okay. I think we're good to go. So happy Wednesday, everyone. Did you know that today is International Happiness Day? A lot of sarcastic laughter. So how are you doing? Good? Happy? Actually, I don't need to ask you because some of you already filled this out for me. Too happy, not too sad right now. But I hope that you are taking good care of yourselves, and I'm hoping that you are kind of looking out for each other, and I think that's really important. So just a couple of other really quick announcements as well. I'm a little concerned about the different quizzes and the way that you're doing these different quizzes. So I think we're going to change things up just a little bit. So I'm going to make both quizzes available on the regular Thursdays, but instead of having a time frame where you have to finish it by Saturday, I'm just going to keep it open until the end of the semester. So until like April 5th, you can do like quiz 4 or quiz 5 until the end of the semester. I hope that makes some sense to you. So there isn't sort of the onus to have it all done in 48 hours. You can actually do it at your leisure. There's really no reason why you have to do it in 48 hours, and I was thinking a little bit about that over the weekend as well. If you are coming in, you can also still continue to come in and ask for a regrade or to have a discussion about your last term test, and that will continue on for the rest of the week between 2 and 3 o'clock. And there is sort of an extra tutorial help session, which we will try our best to stream, unless Facebook goes down for whatever reasons, like just at that exact moment, Facebook decided that it's not going to work anymore, and it was a system-wide outage, and it happened exactly at that time. Bizarre. So that will also be streamed as well. So I'm hoping that everything is good for all of you, and we'll just dive right into what we need to talk about here today. So a couple of things based on what we were last talking about. We were looking at different regions of the brain are particularly vulnerable for excitotoxicity after a loss of blood flow. So you're seeing this loss of blood flow, a thromboembolus, whatever it is, that is causing this lack of blood flow, and all of the neurons that you see downstream are being affected by that. And particularly vulnerable are the neurons that are found in the Purkinje layer, the ones that are found in the cerebellar cortex, and in the hippocampus. And so if we're looking at this pathway, these pathways are actually exacerbated or exaggerated in those particular areas of the brain, which are, again, really important. If you think about what happens after stroke, you often lose motor coordination, you often lose your ability to think well, you lose your ability to remember things, your cognition, motor skills, all of those are affected, and there's a reason why, because of this excitotoxicity model. We also looked at the fact that none of the treatments that we traditionally use for pharmacotherapy, taking a drug after stroke, doesn't seem to work well in humans. And it's one of those really bizarre coincidences that we have great animal models that I'm going to get to in a few minutes, but in humans, none of those successful trials of these different drugs, whether we're talking about voltage-gated sodium channel blockers, whether we're looking at blocking glutamate receptors, or whether we're blocking calcium, they work fantastic after stroke in an animal model, but in humans, not a single one of them has actually worked. And so we need to rethink a little bit about how do we treat this therapeutically and what are our options in terms of the neurobiology and the neuroscience behind that. So here again is this really cool diagram. If you're thinking about this, this is actually one of the coolest diagrams you might ever see in biology, and there are a couple of reasons why. If you were to think a little bit about this slide, I know that you might have looked at it yesterday, or you might be looking at it again for the very first time now. If you were to look at where everything is kind of clustered, where is the different signaling pathways, where are they all converging? It's really not as hard a question as you're thinking of. Like, where are all of these pathways converging inside the cell? Let's make Ken Yip really happy. So what's the powerhouse of the cell? The mitochondria. And in neurons, it turns out that this diagram actually has led to one of the fantastic discoveries related to neurons. And if you read through some of the papers that have come out over the last couple of days, and we're going to talk about some of that very briefly as we go on through this, we're going to be talking about neural stem cells, and neural stem cells might be important. We have neural stem cells. Neural stem cells try to recover your brain after stroke. It doesn't work very well in the long run. But how does a neural stem cell actually control whether it's going to continue to divide or become a neuron? And it turns out that this diagram actually explains all of that. And it turns out that if a mitochondria stuck right in the middle decides that it's going to divide or not divide, actually determines if a neuron will continue to be a stem cell or not a stem cell. And that idea actually came from this, because neurons, when they die, their mitochondria do very, very strange things. So the mitochondria for neurons is sort of an organellar signaling molecule or a platform. So this is actually a much cooler diagram than you would give it credit for. So let's go and take a look at this diagram in a little bit more detail. So again, if you look at the very top, one of the things that we know is we get an excessive amount of glutamate. There is uncontrolled action potential generation. It's one of the reasons why we might be thinking that we could use a voltage-gated sodium channel blocker to prevent the release of glutamate. Regardless, in certain areas of the brain, like the cerebellar